All right, this is the third video on bonding. We're going to do metallic bonds today and begin covalent bonds. But before we do that, the most important thing is you being able to name binary compounds, metals with polyatomic ions, metallic hydrides. So we're going to do a few review before we go into metallic bonds. So, first of all, the most important thing is if they give you a substance, something like this, in order to name that, you have to look at the metal on the periodic table and make sure it only has one oxidation state or one charge. Here's magnesium, and notice it only has a +2 charge. If the metal only has one charge, you just name it. So, this is one charge, this is a +2. Now, so that would just be called magnesium. Now, this is not magnesium sulfur oxide. That is a polyatomic ion. You have to know, and what I tell my kids is, if you detect a polyatomic ion, put it in parentheses and then name it. So this is magnesium. You look on the polyatomic ion chart, that's sulfate. So the name of this thing is magnesium sulfate. That's it. That's all. Now, if it's something like this, same thing applies. Look at the metal. If the metal, and here's the metal, which is iron, but look at iron. It has a +2 or a +3. You got to figure out which charge or oxidation state it is to name it. That has 2, where our magnesium only had 1. So, these are the charges that it could be. It could be a +2 and it can be a +3. Well, how do you figure out if it's a +2 or +3? You got to look and see what it's hooked to. In this case, it's hooked to phosphate that has a -3. So if there's one phosphate with a -3 and there's only one iron, then that iron has to be a +3. So this has to be a +3. +3 and -3 equals 0. And the name is not iron phosphate. You have to tell what the charge is. This is iron, Roman numeral 3. Iron Roman numeral 3 phosphate. That's the name. So you must always look at the metal to make sure it only has one charge. And if it has one charge, you don't need a Roman numeral. But if it has more than one charge, you're going to have to figure it out and put the Roman numeral in the name. Okay. That was a little review on how to name ionic compounds. Remember, ionic compounds, there's 3 types. Metal to nonmetal, metal to polyatomic ion, and metallic hydride. And my rule, if it doesn't contain a metal, it's not an ionic compound. So it has to be a metal hooked to something else to be an ionic compound, which is just a salt. There's only one exception, just one. So, if ammonium is hooked to anything, it's an ionic bond. And it looks like a crystalline solid, which ionic bonds are. So we're just going to do one. The most important one you have to know is this one. That one. Now, I tell my kids, if you detect a polyatomic ion, put parentheses around it if you want to name it properly. So here is ammonium, and here is nitrate. So the name of this is ammonium nitrate. +1 - 1, that equals 0, and that's good. Ammonium nitrate is a wicked explosive. It's a fertilizer for farmers, but man, let me tell you, it's used in explosives, ammonium nitrate. Okay, so anything hooked with ammonium to anything else is an ionic compound. Now we go to metallic bonds. So now, metallic bonds and ionic bonds. Remember, an ionic bond, a metal hooked to something else. A metallic bond, it's just metal. It's just a metal hooked to nothing. So, the definition is a little weird. So, the definition is a fixed positive kernel. Remember, a kernel is the nucleus and all the inside shells. So it's got to be positive because it's not including the valence shell. A fixed positive kernel So, a fixed positive kernel surrounded by a sea of mobile electrons. Remember, metals don't want their valence electrons. So in a metallic bond, the valence electrons are like free to move around, which produces electricity. So, metals conduct electricity because they have free electrons to move around. And we'll do a diagram of them right now. So if these were kernels of Mg, it would look like this. Mg plus 2, Mg plus 2, Mg plus 2, Mg plus 2, Mg plus 2. So these are fixed positive kernels, all right? Now, surrounded by a sea of mobile electrons, well, the plus 2 means it lost 2 electrons. So here are the 2 electrons. 2 there, 2 there, 2 there, 2 there, 2 there, 2 there, and 2 there. So these white dots are valence electrons, and they're free to move around. That is conducting electricity from a metal. Fixed positive kernel surrounded by a sea of mobile electrons. Or they said a diffuse cloud of electrons. It means the same thing. Now, let's go over the properties of a metallic bond. Properties. The first and foremost and most important property is this. Most important property, metallic bond, they conduct electricity due to free valence electrons. They can move around. That's the primary, number one, important property. Number two, remember these three properties? Malleability, or malleable, able to hammer into shapes. Ductile, able to roll into wire. Luster, they're shiny. Okay, those three are very easy properties. Now, number three, from the periodic table chapter, metals are always large atomic radius. So, large size, and if they're big atoms, that means they don't have very much ability to attract electrons, so that means low electronegativity. So, big size means they don't attract very well, low electronegativity. They don't want electrons, so it's real easy for some other element to pull out their electron. That means low ionization energy. And I'm just going to abbreviate low IE, low ionization energy. So large size, low electronegativity, low IE. Now the other ones are pretty easy. Remember, 2/3 of all the periodic table elements are metals. They are either solid or liquid. There's only one liquid metal, that is mercury. All the other ones are solid. Okay, so these are the properties, but like I said, the number one property is they conduct electricity in the solid and liquid state because mercury can conduct electricity. Okay, so when you see this, Cu solid, or if you see this, Cu neutral, this means that they're solid metals. So, Cu solid or Cu neutral, this is what it looks like, right? Malleable, ductile, luster, big atoms, low electro, low IE. Okay, so metallic bond, wickedly easy. It's just a metal. That's all. So when you see that or that, that's a metallic bond. Remember the crazy definition: a fixed positive kernel surrounded by a sea of mobile electrons. And that's it for metallic bond. So here we are, covalent bonding or covalent bonds. Remember, ionic is metal to something else. Metallic is just metal. Covalent, it's between two nonmetals. So remember, nonmetals want to gain electrons. They don't want to lose them. So where did they come up with this name covalent? Well, what's happening is if you have two nonmetals, the two nonmetals, one can't steal it from the other one. One can't steal the valence electrons from the other one, so they have to share them. They may not be sharing equally, but they have to share the valence electrons. So sharing is cooperating. Cooperating with valence electrons. So this word, co, is for cooperate, and valent is cooperate with valence electrons. So covalent bonding, cooperating with valence electrons, it's always between non-metal atoms. And here's the definition. It's a little bit tough. Number two. So, number two, the attraction of two nuclei, all right? In other words, two nonmetals, the nuclei of both nonmetals want to do something, all right? So, the attraction of two nuclei for the same valence electron or electrons. Okay? That is what the definition is. And remember, it is sharing. So, covalent bonding, sharing of valence electrons between two nuclei. All right? All right, that's number 2. Number 3. So, there's 2 ways to share. The 2 nonmetals can share equally. In other words, both of them have the same electronegativity, so one can't pull harder than the other, or they can share unequally. One has a little bit more electronegativity than the other, so it's pulling a little bit harder. But remember, it can't pull the electron completely away. So they are sharing. So we're first going to go over unequal sharing. So, unequal sharing. That means one's pulling harder than the other one. All right, that's A. And we're going to put down number 1 underneath there. I'm going to do this. Unequal sharing means you're going to have a slightly positive end and a slightly negative end. Slightly positive end, slightly negative end, we can think of it as poles, like the North Pole and the South Pole of the Earth. Well, one pole is slightly positive, one pole is slightly negative. So the name of this bond or this molecule is polar, and we're going to call it a polar bond. So, it's unequal sharing between 2 nonmetals. That's going to be a polar bond. Remember, slightly positive end, slightly negative end. Now, there are 3 really, really, really good examples of polar bonding, and we're going to go over them. The first one is this. H2O, all right, which is water. Now, water, the electronegativity of hydrogen is 2.2. All right, not too bad, almost in the middle. But the electronegativity of oxygen is quite strong at 3.4. So if I subtract those, subtract these, and you get 1.2. Now remember, for ionic, it's usually 1.7 or higher. That's pretty strong. So if you look at the electronegativities, you understand that oxygen is going to pull the electron pairs closer to it. So oxygen is going to be slightly negative, while hydrogen is going to be slightly positive. So let's electron dot this. We have O. And then remember, oxygen is in group 16, which means it has 6 valence electrons, which is an S2P4. So we have pair, single, 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 pair. All right? That is oxygen. Hydrogen is in group 1, only got 1 electron. So let's put a hydrogen here and a hydrogen here. Now, hydrogen, I'm going to make hydrogen's electron an X. Now the question is, remember, they share the pair of electrons, but they don't share it equally. Oxygen has a much stronger pull than hydrogen. So the pair of electrons, one from oxygen, one from hydrogen, is going to be closer to oxygen. So it looks like this. There's hydrogen's electron, there's hydrogen's electron. Now, here's the shared pair, here's the shared pair. Notice those shared pairs are closer to oxygen. So that makes oxygen slightly negative. It makes hydrogen slightly positive. Now, in high school chemistry, you don't have to know the symbol for slightly, but we're going to do it anyhow. So oxygen slightly positive and slightly negative, this means this. So that's the slightly sign, slightly negative. For these guys, slightly positive, slightly positive. So, this molecule is a perfect example of unequal sharing of electron pairs. So, if it's unequal sharing, it is going to be polar bonds. So, here's a polar bond and here's a polar bond. Unequal sharing because oxygen is pulling harder. Now, the next thing is this. This has polar bonds, but would it be considered a polar molecule? Okay? Well, here's the way to find out. Polar molecules are asymmetrical. This is a biggie. So let's check it out. If I cut this molecule this way, it looks the same on both sides. But if I cut it this way, there's no H up there, so this molecule is asymmetrical. And what we know is this. If the molecule is asymmetrical, it must be a polar molecule. So H2O has polar bonds, unequal sharing, and is also considered a polar molecule because it's asymmetrical. Now, there's another name for polar molecule. Polar molecule has a positive end and a negative end, and we can call it this also. A polar molecule can be called this. A dipole. So we can say water is a polar molecule, or we can say water is a dipole. And it's just not a normal dipole or polar molecule, it's strong. Water molecules are strong dipoles. Okay? All right, let's do 2 more. All right, the next polar molecule we're going to do is this one. This is ammonia. And nitrogen has a 3.0, hydrogen has a 2.2, so this is 0.8. So this has a 0.8 electron difference. Now, that is weaker than water because water had like a 1.2. So let's electron dot this and see what's going on. So I have an N right here, And then I have N's in group 15, so that's an S2P3. So here's my S2, P1, P2, P3. Now, we put the hydrogens around, one here, one here, one here. Now, these, they're strong, but not as strong as water, so we're going to go like this, X, X, X. Here's your shared pairs. And they're a bit closer to nitrogen because nitrogen has a stronger electronegativity. So nitrogen is slightly negative, the hydrogens are slightly positive. So we're going to go like this. Slightly positive, slightly positive, slightly positive, slightly negative. I won't give you the signs, you saw them in the water molecule. Now, we know that nitrogen is pulling harder, so it's unequal sharing, which means you're going to have a positive end and a negative end. So we have 3 polar bonds from unequal sharing, but now we have to find out if this molecule is symmetrical or asymmetrical. If it's asymmetrical, it's a polar molecule. So let's see. If we cut it like this, the sides look the same. But if we cut it this way, they do not look the same. So ammonia is asymmetrical, which means it's a polar molecule. Okay? That's a polar molecule. We'll do one more. HF. HF. Well, we know hydrogen is 2.2, and we absolutely know fluorine is 4.0. Fluorine is the strongest electronegative element on the whole periodic table. Remember, I call it Rambo. It's the toughest, roughest element on the whole periodic table for stealing electrons. So let's do fluorine. So we got an F. Fluorine is in group 17, the halogens. It has 7 electrons in the valence shell, which is an S2P5. Here's my S2, P1, P2, P3, P4, P5. So fluorine only needs 1 more electron to become stable. Well, here's hydrogen. And fluorine is incredibly strong pull. So it's, looks like this, very close to fluorine. So fluorine is slightly negative. Hydrogen is slightly positive. But look, this is 1.8. And you're going, wait, 1.8? If it's around 1.7 or higher, it's ionic. Well, this is 1.8. Why isn't this ionic? Because what's the definition of an ionic bond? A metal hooked to something else. There's no metal in this, so it can't be an ionic bond. It's just a really, really, really strong polar bond or a strong dipole. Well, let's see if this polar bond, if this molecule is symmetrical or asymmetrical. Well, all we got to do is this. Cut it right down the middle. You got H on one side, you got F on the other. This is asymmetrical. Remember, asymmetrical means, an asymmetrical shape means it's a polar molecule or a dipole. Okay? So we have gone over 3 strong dipoles or 3 strong polar molecules. We're going to do one more. So this one, hydrogen 2.2, like it's always been. Sulfur's only 2.6. The difference is only 0.4. This is a very weak polar bond. So let's electron dot it. Sulfur, group 16, which means it's got 6 valence electrons. Here's my S2, P1, P2, P3, P4. I'm going to put my hydrogen here, hydrogen here. Now, since these two are almost the same, they're going to be sharing it a little bit toward the sulfur. Not much, just a teeny bit toward the sulfur. Because the sulfur is just a little bit more electronegative than the hydrogen. So what that means is sulfur is slightly negative, really teeny negative. And hydrogen slightly positive. So this is a, well, and if we cut it, you see that both sides don't look the same, so this molecule is also asymmetrical. Asymmetrical shape means it is a polar molecule or a dipole. But this polar molecule is extremely weak. So this is considered a weak dipole. All right, everybody understand that? Okay. Now the next thing we're going to talk about, we'll write down some of the stuff I just did, and then we're going to go into what if the molecule, or what if the element shares the electron pairs equally.